All right. Good afternoon, everybody, and welcome to the February edition of the HPC Best Practices webinar series. Today, we're going to hear from Christian Trott of Sandia National Laboratories, and he'll be telling us about modernizing C++ interfaces with concepts, constraints, and stood mdspan, these are all recently introduced or in some cases looking a little further forward in the C++ standard. As is always the case with these webinars, we'd like them to be as interactive as possible, so we encourage you to ask questions. We'd like you to do it using a Google Doc that I've set up, and I'll put the link to this in chat. That way we can get Christian to answer questions in written form that we may not have time for, and we can make that available to everybody to document the whole discussion. We'd also very much appreciate your feedback on this webinar and all the webinars that we produce. And so we have a short Google form to ask you to give us a little bit of comment on this. And finally, if you've registered for this webinar, you will receive an email in hopefully within a week or less when this webinar recording and the slides and the Q&A are published. If you didn't register for this recording and for this webinar and somehow snuck in, we welcome you anyway, and I encourage you to follow the page on the ideasproductivity.org website for this webinar, and you can see when the updates come there. And with that, I will hand it over to Christian.
Yeah, thank you so much for the introduction. And, I'm happy to be here and happy to, what is this? Stop. I'm happy to be here and happy to give this talk. This talk came from, originally somebody had asked me, oh, can you give me an update on all the things which are new in C++? And I was like, starting to do that. And then I was like, yeah, this is probably, more scope for a multi-week lecture series. And I whittled something down to, what I think is some of the most impactful new capabilities for scientific computing, in particular for interface design. So modern C++, right? A lot of the evolution of modern C++, what has been happening there is that we are trying to design interfaces which help you better to prevent and also detect mistakes. Essentially, we are designing things, which help you avoid bugs in your code. You see that with evolutions such as using smart pointers instead of raw pointers, ranges instead of iterators, concepts and constraints, which I'm going to talk about here instead of unconstrained template parameters. And what that really gives you is it gives you enforced safety, enforced correctness. It gives you checkable conditions for the implementations of a lot of these things. And it gives the user or the developer early error detection. And in this talk, I want to talk about three capabilities which are particularly relevant to high performance computing. Obviously, talking about modern C++ features means that this is going to be a very technical talk, right? If you never written C++ code, you probably won't be following very far along. That's just the nature of the beast. Another thing I want to say up front is, a lot of people always say like, oh, C++ is now so big, you can't know everything. And that's also not really how you should think about it, right? You shouldn't attempt to know all of C++. Nobody does, right? Nobody can. It's just too big. It is too capable. It has too many different capabilities. C++ more is a powerful toolbox, right? It has all kinds of capabilities, and you just need to choose the right tools for the right task. And what I'm hoping to do in this talk is introducing some new tools or newish tools which will help you write better interfaces for your high-performance computing codes. So when I think about, the typical, C++ code, how it maybe existed in high-performance computing, I don't know, 10, 15 years ago, right? And I mean, a lot of that code is still around. When, a lot of it looked actually interface design-wise very similar to how BLAS looks like, right? And BLAS is kind of one archetypical software, or library design, interface design in high-performance computing. And when you look at something as simple as a matrix vector add, right? I mean, okay, sure, we stumble first over the name DGMV, clearly Fortran history, right? We only had like, 6 characters or so to name functions. And so we had to do everything in short acronyms. Fine. But then, you see a lot of these arguments coming in, and there's 11 arguments just for a matrix vector multiply, right? There is the argument for whether this is transposed or not. There's arguments for number of rows, number of columns, scaling factors, pointer to the matrix values, a stride value, the pointer to the right-hand side vector, another scaling, another stride value, another scaling value, another pointer, and another stride value. And that design has some conceptual problems, at least, from the perspective of kind of modern interface design. One thing is you have many parameters of the same type, right? It's very easy to switch the order of these things and have something wrong happen, right? If you switch n rows and n columns, it might not even crash your code, right? Depending on how it looks, it might just compute something wrong. You have a bunch of parameters which only together describe your actual data structure, right? The matrix is actually a pointer plus the number of rows plus the number of columns plus the stride. Only in all 3 or all 4 of these arguments together describe what the matrix actually is, right? Or how it's stored in memory. This interface has an implicit assumption of storage order, right? Your metrics better be in column major storage order, or you get, accidentally the transposed answer from what you thought you might get. And you might not even notice that if, num rows and num cols is the same, right? When we just get numerically the wrong value. And there is an implicit assumption in this that the object sizes match, right? Like the number of rows and number of columns value is not getting repeated, right? So you don't have separate values for the sizes of A, X, and Y, right? You get the A values and just assume that X and Y pointers point to memory which matches that in size. And that means there is actually no way for the implementation of this matrix vector multiply to check the validity of inputs, right? The user has to put the right values in, and I can't verify that they are right. I have just to assume that they are right. And we need to do better. So what I'm going to introduce here is I'm going to introduce 3 modern C++ capabilities for interface design. One is mdspan, which is fairly new in the standard. It's introduced in C++ 23. And then constraints and concepts, which are both C++ 20 capabilities. What we gain from this, the benefits of making all of these things more explicit and checkable interfaces are manifold, and it depends a bit on who you are, right? So for a developer of libraries, and also library-like internals of applications, right? I mean, like if you think about a large application, a lot of the internal machinery is actually often structured like a library, right? So the benefits for developers there are that you making assumptions of what your functions take and making this checkable, etc. It helps you self-document. In the source code, it's very clear there what the assumptions are. When you look at the implementation of DGMV, you don't know, right? It's not clear what the storage orders is supposed to be of a matrix, and you might have to dig through the entire loop scheduling in order to figure that out. It also enforces requirements for functions, right? Which is useful, which means that you internally don't necessarily make mistakes. The other thing I'm gonna show is that these new, the things like concepts and constraints help you organize overload sets of functions, and that's very, very useful for interface design. The users of the libraries get more well-defined interfaces, right? The specification of the thing is actually part of the interface. It's syntactically, or partly at least syntactically enforced, right? You don't You don't need to dig through, maybe non-existing documentation or the implementation to understand what are the actual requirements of this function. It also means that certain types of mistakes are caught at compile time instead of, you have to debug it at runtime, what's going wrong. And using these capabilities also will help with AI coding assistance, right? That's something which is obviously coming up really, really fast and everywhere. And lots of people are starting to do that, use AI coding assistance. And by enforcing requirements in interfaces, you do guide code generation, right? It help the compile time errors you get from that help the feedback in the agents, and it essentially helps, with that self documentation, which is implicit in this, right? Helps the AI, directly leverage these libraries, right? Instead of trying to figure out, okay, where do I find the documentation of this? Also look at the documentation, what the actual constraints, requirements, and whatnot for this function are, right? You see that in the code and it's enforced in the code. And so that actually helps it generate, you make use of these libraries and interfaces correctly. Okay, with that, let's start with the first thing, and that's mdspan. So mdspan is finally giving you multidimensional arrays for C++. That was something which was sorely missing for scientific computing, and something which we had designed in Cocos with Cocos views, and which we were able to essentially get into the standard. The properties of these multidimensional arrays are such that the rank of them is at compile time, right? Whether you have a 1D, 2D, 3D, 6D thing, that's a compile time decision. You can mix dynamic and static extents. So you can express something which is a compile time 4x4 thing, but you can also say, like, oh, this is n by 4, right? One important aspect is it has configurable layout. So you can essentially change how the actual storage in the memory is, and I'll show you later an example of why that's important. mdspan itself is non-owning. It wraps existing allocations, so it doesn't have a constructor which actually allocates memory. That was partly a compromise, partly, owed to the last point, and that's that it has reference semantics. Value semantics in high-performance computing are kind of often somewhat useless for arrays because we create a lot of large arrays, and you don't really want to make an assignment a copy of your gigabytes of memory, and you don't want to pass them around to an interface and have that interface make a copy of your thing. So you really want reference semantics, and unfortunately, in C++, we never had the precedent for like having something with reference semantics, which has allocating constructors. So that's why it's completely non-owning. Okay, this is the basic kind of prototype of the mdspan, right? It's a class, it's templated on 4 parameters. Element type, that's essentially your fundamental scalar type, right? It's float, int, double, complex double, but it can be anything, right? It can be your own class. We, for example, in Trillinos and Sandia, we use that where we make views and mdspans of automatic differentiation types. The extents describes the runtime and compile time extents. So that's called like, the basic class for that is called std extents. And this std extents int 5 dynamic extent 4 says you have a 5 by n by 4 3D array with using int as your index type. So you can essentially, mdspan encodes, what kind of like index type you use, whether it's 32-bit or 64-bit. The layout is the mapping from multidimensional index to memory offset, and the accessor describes how you convert essentially a data handle and an offset into the actual access data. There's a reference implementation in the Cocos organization, Cocos mdspan. That's a full implementation. I'll come back later to that. Basically, it backports everything to C++ 17, so you can use mdspan already in current code. Okay, so how do you create an mdspan? As I said, it wraps an existing allocation. So you start with having your data, right? Like at in simplest case, here just race of double. And then what you do is you just hand that mdspan your pointer and give it dimensions. mdspan makes heavy use or can make heavy use of CTAT. So you essentially don't need to provide the template parameters explicitly. They are deduced, from the arguments. So in this first case, right, this is going to be a 2D with 2 runtime dimensions mdspan of doubles. You can obviously specify all this more explicitly. Here, the next one says that I want mdspan of rank 4, where I essentially have like n batched 3 by 3 by 3 tensors. And, hopefully your pointer points to memory, which is long enough, right? So like n by 9. And the last thing is an example where we also explicitly specify that we want the Fortran layout, right? As like a column major storage. So we say we want doubles, we want an n by 8 thing using int as an index type, and we want column major. The default for mdspan is row major, or like layout right, as of a C layout, what you would get for the actual underlying storage if you made like multidimensional C arrays. The default for the index type is size T, so we go with like 64-bit indexing by default. And yeah, that's the basic way of constructing an mdspan. There's many, many more ways and more complex ways for expressing more complex situations, but this is the kind of like starting point. What that means is that it's actually fairly trivial for users if you, for example, you update an C-like interface to using mdspans, right? For users, it's actually not that hard to switch over to that because you can just, like wrap your existing arguments into an mdspan. So say you had a function matrix norm, right? And your function was looking kind of like, BLAS-like. You give it a pointer in 2 dimensions. What you would do is you would essentially just tell your user, yeah, now you can, wrap that into an mdspan, right? You just say that and that works. And now it's passing an mdspan in. So accessing data on your matrix, on your mdspan happens via the square bracket operator. So you use that square bracket, right, with like 1 integer or integral argument per index. It's actually a bit more powerful than that. You don't have to use integers. You just have to use something which is convertible to the index type, which means you can even like use like, your custom index types, which just convert internally to like, say, int or size T or something like that. One thing which is important, I said that this mdspan has reference semantics. So assignments, etc., are shallow, right? But they follow kind of like pointer behavior. For example, here, the first matrix, I created that as a matrix of double, non-const double. So I can assign to it. But as with pointers, right, where you have pointers of const data and of non-const data, you can assign that matrix to a const version of itself, right? Where you essentially specified in the template arguments of the mdspan that you want to look at const data. In that case, const matrix, you couldn't assign to it anymore, right? You could only read from it. Another thing you can do is there's all kinds of conversions which work. For example, in this case, I'm saying I want also an mdspan type, where I explicitly made the dimensions or the extents compile time. And you can assign from runtime to compile time, but it will potentially in debug mode, for example, check that you're actually not making mistake, right? If n and m is not 4 and 4, then this will fail. The other direction always works, right? You can always assign from compile time extents to runtime extents because you just, it just sets the the runtime extends to the compile time numbers. Another thing you can't do is, and that's why that's important, right? The layout, you can't just change the layout, right? So I said the default layout is layout right, the kind of C style layout. So if you try to assign that matrix up there, which has the default layout, the layout right, to an mdspan of layout left, that will not compile, right? So you can't accidentally try pass things around. And generally, the way to think about it is that, if logical stuff represents the same data, right, and it doesn't violate these kind of pointer const rules, the assignment will work, right, or the copy construction. And in the cases where it's clear that it always will work, right, there is no kind of like error checking necessary, right? It will never throw. In the cases where you could make a conversion which only under certain circumstances will work, right? There will be debug tests for that. So what does that mean for the impact on usage, right? Say you wrote your matrix norm but you said my matrix norm will only work with layout left, with kind of column major storage, right? You would write that and say like, okay, I'm only reading from that matrix, so I'm doing const double, right? So you can pass const data into it. The dims here is a shortcut for I want an extends with two dynamic extends and size t as the index type, and the layout left then for the column major. Now, when a user passes in a non-const one, that just gets converted, right? If a user passes in a const one with compile time extends, that also works, right? It just gets passed in. What doesn't work is the user trying to give you a matrix in row major storage. That will not compile. And that's the power of like this encoding these kind of informations in the interfaces better, having these data structures being more explicit. It means that your assumptions, right, about things are actually encoded in an interface. Now, within your matrix norm, you could now call the CBLAS, right? What you did is you wrapped the safer interface around whatever your implementation looks like. And that's fine, right? The most important thing is that your interfaces expresses what the requirements are of your actual implementation. So I said we have layouts, right? And that these layouts matter. One example for that is a simple matrix add, right? So this is using a Cocos example code, so don't worry about it. The Cocos parallel 4 just says, parallelize over that extent here, right? And it launches a thread for each of these things and then runs the inner iteration. So this is essentially just a double loop, right, to do the matrix add. But if you compile that for an NVIDIA GPU, right, and for a CPU, you will see interesting behavior depending on what layout you chose. With layout right, the performance is actually way, way worse than with layout left on NVIDIA GPUs, or generally GPUs. But layout right is the better layout on CPUs. And that's because the data access pattern changes. And what you want is on GPUs, you want this with adjacent threads, in your parallelization scheme where access adjacent memory. So essentially you want the I being consecutive in memory. On CPUs, you want, cache lines being loaded in and then hit, the next memory access hitting the same cache line again. So what you want is prefetching, fault sharing shouldn't happen, etc. Which means that your contiguous access should be in J, in the write access. And that is a very important aspect of what mdspan lets you do. You can change the storage order of your thing by changing a type, right? Which means you could have applications with like a configure file where you configure what your types are and you change that depending on the architecture you're on. You don't need to change your algorithm. You can change your underlying storage order. And that was a big part of the design. Another thing I said is there was this accessor argument. And I said something about like this accessor, what it's going to do is it essentially takes your data handle, your pointer, it takes an offset and it converts it into the actual data access. The important thing about it is that the pointer is not necessarily an element type star, right? It can be something more complex. It can. We have even like prototype things where that thing is actually a MPI window handle, right? And the mdspan would access, potentially even remote memory. Also, the element type, as a reference type, is not necessarily just a standard reference, right? It can be some kind of like proxy type, which then has implemented operators, etc. We use that, for example, for automatic differentiation type, ensemble types, and so on and so on. And so the access function doesn't necessarily need to return the pointer dereferenced, right? It just somehow generates from whatever that pointer thingy is and the reference. One thing you can use that for, which is really useful in our case, is for heterogeneous computing, is you can use type-safe memory space access. Now, the element type and the pointer type is just standard things, right? But what the access function can do is it can essentially check whether you are actually on the GPU while you're trying to access that. And if not, throw an error. That way, your mdspan, which uses this accessor, can catch when you try to access the memory from the wrong side, right? And thus prevent, invalid dereferences. That concept with that accessor, right, using it in that way, also means that you can write multiple overloads of your function, of your interface, depending on where the memory comes from, right? You have a set of like accessors, and we have these, for example, in Cocos. And you now would have one overload of your matrix norm, which takes, a thing where accessor is a GPU accessor, and one where it's a host accessor. And that way, the user can, if they give you a right mdspan, it will select the correct overload, and you can dispatch to, say, QBLAS in one case and CBLAS in the other case, or MPL or something like that. Another ability which is kind of important, right, in C++ land or in HPC land is that you can slicing and dicing, right? I mean, Fortran can do that, right? Python can do that. Everybody can do that. C++ couldn't do that, and now it can. And that's called sub-mdspan. So you hand sub-mdspan your mdspan, and you give it slices. And there's 4 different types of slice arguments. There's an integral, which just gets you a single thing. You can pass in essentially a pair, which gives you a range, so half open range. You can pass in the full extent keyword, which is an actual keyword, right? Or not a keyword, but it's a thing in the standard library, which indicates that you want all the elements in that, kind of like the column in Fortran. And there is something called a strided slice, which essentially allows you to say like something like, I want every other element. There's a couple examples here, right? You start with this matrix, getting a row. And I again forgot to fix that. No, yeah, this is a row, yeah. Getting a row, you pass in, a column index, and you say full extent for the row index, for the other way around. You pass in a row index, and you say all the columns, right? And then you can, do things like chose a set of columns, right? So that's returning a 2D mdspan. The first one is returning a 1D mdspan. And you can do things like slicing, right? Or with strides. In this case, you even get compile time extents back, right? So the thing you get handed back actually has a compile time extent because it can deduce from your arguments, that you passed in compile time thingies. All of this is available in different shapes or states. C++23 came with std-mdspan, with std-extends, the layout left and right and stride, also some basic layouts. That's implemented in LLVM. It's implemented in GCC 16, which is the next kind of GCC release. It's in the trunk. And MSVC has that as well. The sub-mdspan, so the slicing and dicing plus some new layouts are C++26. They are in this already implemented in the trunk in GCC, but not in the other ones yet. We hadn't time to fully upstream that. If you don't want to wait, right, then, or you need this thing to work on GPUs, which, might be not unlikely, you may want to go to our reference implementation, which also backports it to C++17 and C++20. It doesn't require anything else from Cocos, so you don't have to buy into the Cocos kind of programming model in order to use that mdspan. It supports CUDA, HIP, SYCL, etc. One difference is if you are in C++17 or 20 mode, you have to use the parenthesis operator instead of the square bracket operator for data access, because square bracket with multiple arguments does not actually work in C++17 and 20. That's the C++23 language feature. But that thing is well supported. The Cocos mdspan is what we use underneath to implement Cocos View at this point. So this is used in, millions and millions and millions of lines of production code. Speaking of Cocos, Cocos View has interop with that. So there is constructors for views from mdspan. There is, conversion operators in View to mdspan. There's an explicit to mdspan function. To get an mdspan from a view. So there's essentially full interoperability between view and mdspans. You can convert and assign them the same as, between mdspans themselves or between views themselves, right? So all of that works perfectly fine in Cocos 5 if you happen to be a Cocos user. Okay, with that, let's come to constraints and concepts. Everything I'm going to tell you here, I'm going to use mdspan as kind of the class I just introduced as an example, for leveraging or constraints and concepts. That works obviously with any other.
Did we lose Christian?
I did.
Yeah. I'm not seeing him. Hopefully he can sign back in. I'm going to pause recording. Yeah. I think we need to go back to that slide. Yeah, I think that's where we lost you.
Yeah. Okay. So I was saying that all the stuff I'm going to say here are applicable to Cocos View the same way as to mdspan. Basically, everything works one-to-one more or less with View as well. But obviously, it applies to any other kind of like classes, complex classes as well, right? So constraints and concepts essentially are mechanisms which help you build function overload sets and also enforce requirements on the functions and their template parameters. Constraints is really replacing things like sFine mechanisms. If you wrote complex interfaces, you've used that a lot in the past in C++. It makes it easier to build overload sets. And one nice thing is it can be used on non-templated class member functions. So, where sFine did not actually work. Concepts are in some ways an extension of that. It essentially allows you to express requirements for type or multiple types in combination. So you can essentially combine constraints into like one nice, handy shorthand. So the basic constraint thing is introduced via what is called the requires clause. What that does is it expresses constraints and requirements on your function. With the most important usage in my mind is being that you get rid of clunky sFine mechanisms. So here's a simple example, right? So I want this function print elements which can print elements, and you want one overload for rank 1 views or mdspans and one for rank 2. And before that, you would have essentially done something like the svine thing here, std enable if you use that mdspan condition, that the rank is true there. And if you know what enable if t does, right, you know that means it's actually compiling down into a void type, or it compiles down into essentially an error or failure to work when the rank is not 2. With the concept require clause, you replace that with requires clause. You say requires, and in parentheses you put the conditions on what this function overload requires to of their arguments to satisfy. And that's basically all, right? Now, you can put all kinds of conditions in there, right? They need to depend on the template parameters, also the conditions, but you can put all kinds of stuff in there. You can even put things in there, where I'm coming later to, where you can put expression checks, etc. in there. Now, with concepts, it allows you to pre-package a bunch of these things. Where does it? I hate that when it's in the mode where it goes forward on its own. Okay, with concepts, you can pre-package a bunch of these constraints at the same time. In some situations, you can use them almost like a type. The use of that comes in particular, when you had like complex templated classes, functions, right? Like, for example, this thing, right? If you want to take a generic mdspan, right? But it needs to be an mdspan. You say you template your function on all the template parameters of mdspan. That looks ugly enough if you have only one mdspan argument. If you have like, 3 arguments, 3 mdspan arguments, you're now having your function now needs 12 template parameters, right? And that's kind of annoying. With concepts, we can do something where we essentially say that what you take is an mdspan instance. That's the concept. And A needs to be an mdspan or fulfill that concept in order for that function overload to be considered. How do we get to that? We start with essentially type traits, right? And we start with like just a template value here. By default it's false, and when we have a partial specialization or a specialization of that, which says that if you give me a type which is an mdspan, then it's true. Now, where do we go from there? So with the already introduced requires clause, right, we could just use the requires clause with is mdspan instance, right? You template on t and you just require that t to be that type trait is true. But what we can do is we can define a concept which essentially just says, essentially you are that type trait. With that, we can do 2 things. We can either use that concept instead of the class keyword and say like t needs to be fulfilling that concept, or we can directly use it instead of that t, and not template the function. Both of those are valid. That obviously is, quite a bit of an improvement over having 4 template parameters, in terms of like readability and so on. But the real benefit comes when you have multiple arguments, right? Like, say I'm taking 2 mdspans, right? I said, well, now I need 8 template parameters. But the nice thing about the concept is that a concept is not a concrete class type. So if we use the template variant of that and we say that both T1 and T2 need to be mdspan instances, right? They don't need to be the same mdspan type. They can be different mdspan types. And the same thing can be done in the non-templated way, where you say this concept, you use that concept with the auto keyword together. And now A and B still don't need to be the same mdspan type, right? They can be different mdspan types, but you don't have to like have these 8 template parameters anymore. And that makes this kind of like really improve, readability and whatnot of your functions. And it expresses still that this has to be an mdspan. Now, before I go in a couple more complex use cases of concepts, one thing I want to do is I want to compare that to ifconst_expr. So ifconst_expr was something which allowed us to already replace certain asfine usage in C++17. So essentially, it's like compile time conditions where you have kind of compile time branches in your code. And while we have now concepts and requirements, require clauses, right? ifconst_expr still has its usage, right? It's not, as I said before, it's a toolbox, right? You need to use the right tool in the right place. The nice thing about ifconst_expr, right, the way I used it here on the left side is there's a ranking of choice, right? If these choices are not kind of like mutually exclusive, you essentially can build this kind of ranked choice thing. That is something you can't do with overloads, right? The overloads need to be completely disjoint because otherwise you get ambiguity when it tries to choose which overload to use. You get a bit with ifconst_expr, you have a bit better control over all the variants. It kind of looks usually all in the same place, and you avoid duplication of common code, right? If in the place of that static assert there, you have a bunch of like things happening which are common no matter what the rank of your mdspan is, right? If you wrote multiple overloads, you would need to kind of, either put that into an extra function, which then gets called by every one of these overloads, or you duplicate that code. And yeah, one nice thing about having the different overloads is that you can put them in different files, right? So it might help code organization for more complex use cases. The important thing is use the right tool, right? Don't just say, oh, I know this or I know that, use the right tool for the right case. There's a bunch of concepts in C++20. Most of those are kind of correlated to, type traits and whatnot. You can look at that. I would expect that many of these are more useful for very low-level libraries like Cocos than implementing complex data structures than most HPC code. But there are some. Okay. Before I come to an end, I want to introduce one more thing, and that's requires expression. So far, right, we only checked essentially Boolean expressions, right? We checked like, is this type, right? Is this of a certain rank and stuff like that. But with concepts, you can actually do more, right? Or with constraints, you can more. You can use this require clause to, as this requires expression inside a requires clause to check that a certain type of expression is valid. So what that does is you have the requires clause in which you stick a requires expression. That requires expression can take variable declarations and then the actual expression you want to check that that's valid. And here's a simple example of that. So I make that function set elements and I want to take any view-like thing, whatever view-like means, right? Any kind of thing into which I can index into with two integer indices. And I can assign whatever the second value is I'm passing in. And the way I do that is I say like, I'm having a requires clause with a requires expression. I'm going to use 4 kind of, arguments here, or, kind of dummy arguments. The view-like thing, view, a value, and two integers. And then I can say the expression view ij equals v. And this thing will essentially now only be a valid overload for a view-like, for any type of view-like, if that expression can be validly formed, right? And that means, for example, in Cocos land currently, right, with the C++ 17 and 20 mdspan implementation, which uses also the parenthesis, this function would be valid for both a Cocos view and an mdspan, right? Both of them would, if they are of rank 2 and they are non-const. You can pass them in there and it would work. Now, you can also combine these things into more complex thing, right? Like say we have this concept of there's two things and I can add them with plus equal. I call that addable, not with an E. Not to eating, right? It's to add things. You can combine that with mdspan, right? I say like now I want an addable mdspan, and that's takes two class arguments. Both of them need to be mdspan instances, and the element types themselves are addable. And I can do that also with like multiple kind of like conditions, right? I could have built that individually instead of like recursively via the already existing concept. And now you can use that, right? I mean, maybe I want to check other things like that they are also the same rank, for example, etc. There's all kinds of stuff you can add, but that is really the power where, these concepts allow you to express very nicely, all the requirements or a lot of the requirements on your functions. And using that in your interfaces means that stuff is checkable. It's relatively easy also for AI things to discover, what the conditions actually are on your thing, right? It can reason much more about, oh, you want a class and that class needs to be an mdspan and it needs to be a rank 2 and blah, blah, blah. Then there's a pointer in integers, right? Now, concepts have a bunch of pitfalls. One of them is that concepts have kind of the effect of introducing public customization points, right? Anything fulfilling that requirement of having the operator I, j, being assignable to, will match that concept I introduced or that requires clause, right? I had earlier. Do I really want that, right? What if that, parenthesis operator doesn't actually do an assignment thing, right? What if it does all kinds of like random side effects, right? You really need to think about whether you really want to introduce that public customization point, because the problem is that if you change your concept, you change overload sets, you change what matches the thing. That means both adding and removing requirements is actually problematic. If you add a new requirement, some user type might not anymore match the thing and not be a valid thing anymore, for that function overload. And now, your stuff, your user code breaks. If you add or take out a requirement, you might introduce new ambiguity, right? Like, for example, if you added or you took out a rank requirement, right? When now suddenly on the user code side, you might have, ambiguity because they had another overload which just didn't have that particular rank requirement, right? And that's the real problem, right? Generally speaking, concepts that include this is a specialization of this template, what I did with the mdspan instance concept, those are pretty safe, right? Because you're just saying this has to be an mdspan, right? And even if you change mdspan, it still has to be an mdspan, right? That doesn't break it in ways, which is different from how like, the kind of template way of just taking an mdspan worked before. So generally speaking, I'm not super concerned about concepts like this is a rank 2 mdspan instance, right? Which says it's an mdspan and it has rank 2, right? These kind of things are fine. As long as the concept includes that, it's generally speaking safer, right? Okay. There's a bunch of other things, in particular in C++20, which might be of relevance to you guys, which would be useful to potentially look into. There's things like coroutines, right, that express asynchronicity in a different new way. It's really useful for things like task systems, event-based systems, etc. But the problem is right now, I think there's relatively limited support for it on GPUs. So, might be of limited use for all of us, who have to deal with the fact that we have to run our code on GPUs as well. Obviously, using that introduces a lot of added complexity, right? I mean, if you add asynchronous programming concepts to your application, it gets more complex, right? Ranges library is kind of really cool, right? It's composable iteration over kind of collection of elements. It's a huge thing. Definitely needs its own presentation. Stud format is kind of really cool, right? It's like much better way of like dealing with formatted output. In particular, it has customization points where you can essentially define how your own print stuff works, or your own types print. It's type safe, right? It doesn't have the overflow problems of like printf and whatnot. So it's kind of really cool. I saw in the chat here there's a question if can stud format be called on device. Unfortunately, as with everything else, right? Like nothing in the standard libraries can, yeah, okay, can really be called on device, right? Stud format in particular is partly problematic. Now there's workarounds, you can, if these functions, and a lot of them are const expr, you kind of can call them. On NVIDIA, you get warnings if you maybe, and you might need to use that experimental flag for enabling const expr calls. But it's, the short answer is no. The long answer is yeah, maybe. But I think we as a community need to fix that, actually invest into making the standard libraries usable on device, right? That problem, for example, applies to stud_span, right? It's a super simple version of mdspan, just 1D pointer, a static or dynamic extent. And, it's not really usable on device, right? Math constants is kind of cool. Like how many codes do we have which define pi? Probably a lot. Maybe we should, stop that. And modules is a really cool thing as well. That's a capability which helps with compile times. Cocos, for example, in Cocos 5 with Clang on CPUs, about 15% improvement of compiling all the Cocos tests if we compile in module mode instead of in, header include mode. Worthwhile to look at, but again, it's supported in LLVM with like if you use Ninja, but it has kind of problems. Okay, questions. If you want to use Cocos mdspan, for example, etc. One thing is join our Cocos Slack channel, and we can talk there. All the the majority of authors of the core kind of authors of mdspan and whatnot are there. There's a whole bunch of people on the Slack, who know concepts and constraints pretty well and are on the C++ committee. So if you have questions, even if you're not using Cocos itself, feel free to join us and ask questions there. And with that, we'll have a few minutes left for questions here live.
Yeah, great. Thanks for a wonderful talk, Christian. We have received a lot of questions, and Mark Homan has been very gracious in making some comments and providing at least partial answers to many of them. So I'm going to try to go through first some of the questions that he hasn't hit yet, but we'll get to as many as we can. And Christian, if you can stay on for a few minutes, we will continue as long as we're able.
I can go a few minutes over, for sure.
Yeah, and we'll have the recording and we'll have the Q&A document. So first of all, please make some comments about how to limit the complexity and improve the understandability of compiler error messages through the use of constrained templates and concepts.
So compilers, as modern compilers, got already better with like canonical use of sphene, substitution failure is not an error, right? And started getting better errors. But the nice thing is now that if you do error messages with concepts and requires, right, the error message you get are significantly clearer, right? It's telling you, oh, I found this overload, but I can't use this overload because this particular constraint is not fulfilled, right? Or this concept and this particular part of the concept is not fulfilled by what you are trying to give me, right? When you try, for example, in a function which says the mdspan has to rank 2, right? And you pass a rank 3 in, it will tell you, I can't do that because your rank is 3 and this function only takes things with rank 2, right? So that that really, really cleans up error messages, right? You don't get some random template error thingy, right? You get fairly nice error messages. I had a bunch of Godbolt examples in there. Maybe I'm gonna post them. I don't know, maybe I can post them in the chat. That lets you a little bit experiment with that. It's really much better.
All right. There are a few here that Mark answered. I'm going to skip past. The next question I'd like you to respond to is, would you consider using DIMS instead of dextents in future presentations? DIMS is shorter and has better defaults. And there's more to the question, but I think that's enough to get you going.
Did that question come from Mark?
I don't know.
Yeah, it did.
Oh.
Yeah.
I love you, Christian. You're great.
Yeah, and my answer is I used it in a couple places, but I don't think it's the greatest default because it makes your GPU slow.
No comment.
What? Yeah, DIMS essentially doesn't require you to tell the index type, and it uses size T by default. But the 64-bit integer throughput on NVIDIA GPUs and also like Intel GPUs is a very small fraction of their 32-bit integer throughput.
You just put int at the end. You put it at the end.
What?
Dims 2, comma int.
Yeah, I mean, then I can also say dextents int, comma 2, right?
Oh, okay, but, yeah, you do you, babe. You do you, man. It's all good.
Yeah. Okay.
All right. How does the requires expression provide stronger guarantees than standard templating? As far as I'm aware, syntactic validity is already a requirement for a template overload to materialize.
So it does work kind of like sFine, right? Like it works pretty much the same way on that front, right? But you can use requires clauses as I feel it's a bit cleaner than using sFine. For example, a lot of people, what they did is they kind of introduced extra arguments to use with sFine, right? Extra template arguments and whatnot, right? There's all this shit, where we wrote like, stood enable if t, default the template argument, with an int star as the thing or whatever, and defaulted to 0 or something like that, right? There's all kinds of random ways of where requires clause is just syntactically a bit cleaner. It doesn't really conceptually make it much safer than sFine, right? sFine is perfectly fine from a safety perspective in that front as well. You can, however, use requires clauses on, for example, non-templated member functions, which you can't do with sFine. You would still need to use a template argument, a template parameter from the class itself. But based on the template parameter of the class, you could, for example, have two non-templated overloads of a function, one saying, I'm only working if you passed in a rank 2 mdspan into my class, and the other one if you passed in the rank 1, right? Does that make sense? I hope that answers the question a bit.
Yes, if I could clarify, I think I was talking about requires expressions, like the requires, but I think that Mark talked a little bit about that in the Q&A.
Yeah, you can't really do that with sFine, not that way.
Well, I thought that if you have like, matrix A, matrix B, and then in the body of your function, you try to say like, A elements ij plus equals 1, or you had set equal to
no.
now.
If you say that in the body of a function, that is not part of sFine, right? That is not considered, as the body of a function is not considered during overload selection.
Okay.
Right? And so you absolutely have to do that in this requires clause in order to eject it at overload selection, right? It would select that overload and then it would fail to compile.
Okay.
Make sense?
Yes, thank you.
All right. What would be a non-invasive way of checking that concepts work as intended in unit tests? Is there an elegant way to check that the correct function was called, or should outputs or side effects be tested instead?
I mean, you want to check that you hit every overload, right? And I mean, some, also like, coverage checks, for example, can check that, right? Checking that you actually hit the right overload, I'm not sure that there's a real way of doing that, right? I wouldn't necessarily be aware of something. We do some of the stuff, we do some random stuff in Cocos where we have, where we use our tools interface to check whether we go through the code paths we expect. Where we essentially write a tool which then hooks into kind of like, customization points of our runtime to provide output, and we check for the expected output in our tests. But just in general, that's not a thing, right? You can't really figure out which overload was called.
All right, we have a comment in the chat from Chris Green who says testing, it's not easy, but compile time testing is possible in CMake.
Yeah.
T-verify that unwanted arguments are actually barred as expected.
Yeah, you can write tests which essentially check that if you have something where there shouldn't be an overload, right? Because you said I only have an overload for rank 1, rank 2, rank 3. You can do things where you can test that if you pass a rank 4 in, it fails to compile, right? I mean, that's possible. And like the LLVM standard library, for example, does that actually fairly extensively. We have these kind of tests where they check for expected compile time failure, right? So like where they even they check for the correct error message from a compiler. So that is possible, right? What's not possible really is to check that, in this test I hit that overload, right? That's kind of iffy. But thanks, Chris.
Right.
Yeah, it's a good practice. If you can do it, it's complicated and it's a lot of work, but it's a really good practice to check that, if you give the wrong thing, that it compile time errors out.
Okay, let's try to hit a few more here. Is C++ 20 moving to mostly header-defined libraries similar to just-in-time compilation like in Julia? Precompiling libraries seems to be a combinatorial explosion.
C++ itself is almost all header only, right? Like there's relatively little pre-compiled stuff because everything is templated, right? I mean, it's called the STL, the standard template library, right? For a reason. So C++ itself is mostly headers, right? Anyway.
Okay. Here's maybe a bit of a philosophical question. What's the main advantage of using mdspan?
So the main advantage is that it's probably the most concise and complete expression of what the how an actual multidimensional array is stored in memory, right? It's a full description of both the memory layout and the extents, and it's at compile time, which means that you can reason about it and check for it at compile time that your expectations are met, right? And what your requirements are on your function interfaces.
All right. And a couple of related questions, questions related to the Cocos mdspan implementation. One is that the last release is about 3 years old. Would you mind creating a new release to get the latest fixes into conda spec, etc.?
Can you repeat that for a second? Sorry.
The latest release of Cocos mdspan is about 3 years old. Would you mind creating a new release to get the latest fixes out?
We are planning to do that. I mean, you can get a de facto release and tested version from the Cocos library itself, right, where we repackage it. But we are planning on doing a release really, really, really soon. Promise, fingers crossed, kind of hard.
We'll hold you to that.
Yeah.
And then would using Cocos mdspan with more recent C++ standards, but obviously compilers who don't have stood mdspan, allow the use of the square bracket syntax?
Yeah. In C++23 mode, it's enabled.
All right. So that covers the main questions. Mark, helpfully responded to several things, which I don't think we'll take the additional time to go into here. But Christian, I will ask you to sort of look over the answers, and we've had also helpfully somebody trying to transcribe some of the more recent answers, so that'll be great. But we'll get these all written up, and we'll get the recording and the Q&A and the latest slides out to everybody as soon as we can. So thank you all very much for attending, and thanks to Christian for a great and very informative talk.
Thank you. See you guys.
Thanks.